Hello everyone. In the past few videos we gained the skills so that we can finally go ahead and solve exponential and logarithmic equations. We'll start with some exponential equations and then we'll work our way to logarithmic equations. Before we solve either type, we want to review both the laws of exponents as well as the laws of logarithms. And of course, we have the product rule for exponents, the product of two powers of the same base. We keep the base, add the exponents. For the quotient of two powers with the same base, we keep the base, subtract the exponents. When we have a power of a power, we keep the base and multiply the two exponents. Then we have the zero exponent rule, which says any number to the power of 0 is 1. Of course, the only exception would be 0 to the power of 0, which is undefined. And these are the negative exponent rules. We've learned that b to the negative n is 1 over b to the n. 1 over b to the negative n equals b to the n. And when you have a fraction that you're raising to a negative power, you can go ahead and flip the fraction, reciprocate it, and then raise it to the positive version of that exponent. We've also studied these properties of logarithms, starting with the definition of a logarithm, which is the most important, because if we don't know that, we can't do anything else with logarithms. And of course, we remember that when we say y equals log base p of x, the logarithm is just the exponent you need to raise the base to get the x, the what's called argument. So b to the y equals x. Then we had the product rule for logarithms. The log of a product is the sum of the logs. The quotient rule, the log of a quotient is the difference of the logs. The power rule, which the log of a power is the exponent times the log. We've seen how this plays a particularly important role because it's the one that can take an exponent and legally turn it into something other than an exponent. We haven't had any other rule that does that. Then we had the log of 1 rule for any base. We know we get 0 because any base to the power of 0 is 1. Log base b of b itself, of course, will be 1 because b to the power of 1 gives us 1. And log base b of b to the x equals x because b to what power it becomes b to the x? Obviously x. This one comes right out of the definition of logarithms. In this equation here, if we take y and replace it with what it's equal to, which is log base b of x, we get b to the power of log base b of x equals x. We will also be utilizing these 4 facts that have to do with the fact that not only are both the exponential and logarithmic functions, they're also one-to-one functions. The first fact that if you have basically x equal y implies b to the x equals b to the y is just justified by the fact that the exponential function f of x equals b to the x equals is a function. So if you have the two inputs that are the same, the outputs must be the same, and no input has more than one output. This fact, which is the same one going in the other direction, which says if b to the x equals b to the y, then x equals y, follows from the fact that f is 1-to-1. So if you have the same output, they must have come from the same input. Same here with the logarithmic function. If you have two equal inputs, the outputs of the log will be equal, obviously, because the logarithmic function is, after all, a function. And if you have two equal outputs of the logarithmic function, then the inputs must have been the same. This has to do with the fact that it is, of course, 1-to-1. So we'll start by looking at some exponential equations. We already know how to solve exponential equations of this type, where the two sides can be written as powers of the same base. So for example, here we know that we can use base 3. We can write 9 as 3 squared. We can write the 27 as 3 cubed. Then we apply the power rule on both sides. and we end up 3 to the 4x equals 3 to the, here of course we have to distribute 3x minus 3, so we get based on the fact that if b to the x equals b to the y, that implies x equals y, we end up with 4x equals 3x minus 3. Again, realize we're not canceling the 3's or anything like that. This is a very sophisticated deduction based on the understanding of the fact that the exponential function is 1-to-1. So now we go ahead and get the x's on one side, so we end up with x equals -3. Now, the process we just went through will not work with an equation even as simple as this one, 3 to the x equals 10, because we cannot write both sides of this equation using the same base. For this, we're going to have to use logarithms, as we'll see on the next screen. So we're going to need to keep in mind a couple of facts that we discussed already, that if we have x equals y, then the log of both sides must be equal, and the fact that the log of a power is the exponent times the log. So let's see how we will utilize those two facts. So starting with our original equation, we see that the unknown is in the exponent position. We have to bring it out of that position if we have any hope of solving for it. The only rule we have that helps us do that is the power rule for logarithms. So that's why we have to do what's called take the log of both sides. Again, this is a advanced operation that is being done on both sides of the equation. It's not one of the basic 4 operations: add, subtract, multiply, divide, but it works because of the fact that the logarithmic function is indeed a function. So we take the log. Now, which base we take makes absolutely no difference, but normally, because calculators usually only have base 10 and base e on them, normally we either use base 10 or base e. If the problem happens to have a 10 as one of its side or a power of 10, it's usually better to go ahead and take log base 10, even though ln will work correctly as well. So here we'll go ahead and take log base 10 of both sides. We end up with an expression looking like this. Again, we don't write the 10s, but we know they're sitting there invisibly. So I'm just putting it in for clarity. So on the left side, we just go ahead and bring the x down using the power rule for logarithms. So we get x times log of 3 equals, now on this side, if you notice, we have log base 10 of 10, which is of course 1, because remember, when you see this, you ask yourself, what number do I raise this base to the power of to get this argument? And the answer, of course, here will be 1. So this is 1. So we end up with x equals 1 over log 3. Now, this is an exact answer. Should the problem require a decimal answer or an approximation, then you just plug it into a calculator. So here we just carefully type in 1 divided by log 3. So we push the log button and then just push 3 and enter. So there it is. So the answer is approximately 2 or 2.0595 if you want to be a little bit more accurate. Let's go ahead and double check that. 2.0, we need to fix that. It's 959. So it's a good thing we checked it. 0959. Now, this is an approximate answer and this is an exact answer. Now, it is good to make sure that this makes common sense when possible, when the numbers are not that large. Notice, we know that 3 squared is 9, right? So to get 10, we shouldn't be going all that much above 2, correct, for the exponent. So this does make very good sense. So that's how we solve basic exponential equations that cannot be solved by making both sides powers of the same base. By applying logarithm to both sides and using this rule to release the exponent from its position as an exponent and making it a factor so that we can then work with it. So here we have a similar scenario, but a little bit more involved. But we can still use the exact same technique. We can take the log of both sides. So we'll start by doing that. So we get log of 2 to the x minus 1. I'm obviously taking log base 10 of both sides. We have to, of course, take the same base logarithm of both sides. So now we're going to use the power rule to go ahead and bring the exponents down and make them factors. So we definitely will need parentheses here because there's more than one term in the exponent. So we get x minus 1 times log 2 equals quantity x minus 1, that is. And on that side, we get quantity 2x plus 3 times log 5. When you don't want to say open parentheses, write something, and then close parentheses, you just say quantity. So the moment you say quantity, that means a parenthesis is opened. And the moment you mention another operation, so you say quantity 2x plus 3, and then as soon as I say times, that means close the parentheses and go into multiplication mode, and then whatever comes next. So now we're solving for x, so we're going to go ahead and distribute so that we can eventually separate the x's and take them to one side. So we have x log 2 minus 1 times log 2, which is just log 2, equals 2x log 5 plus 3 log 5. So now we want to get all the x terms on one side and all the constants on the other side. And of course, if there were any combination possible on either side, any simplification, we would have done that first, always. So, but we don't have any like terms on either side, so we go ahead and move the x's to one side. Let's go ahead and take them to the left side. So we have x log 2 minus 2x log 5 equals, on the right side, we have a 3 log 5, which stays. We move the negative log 2 to the right side. It becomes positive log 2. Now, since we're solving for x, we're going to have to do something here, which is of course going to be factor out the x. So we get x times log 2 minus 2 log 5 equals 3 log 5 plus log 2. And now all we have to do is go ahead and divide both sides by this factor, this complex factor, to get it by itself. By complex, I mean more than one term. I don't mean a complex number. All right, so we end up with x equals 3 log 5 plus log 2 over log 2 minus 2 log 5. Now, if we want an exact answer, we can stop. If we want an approximation, we'll go ahead and use a calculator carefully. Now, we will want to utilize parentheses. So I'll go ahead and contain the entire numerator in a set of parentheses. So let's see. All right, so we'll go ahead and start with 3 log 5. It opened some parentheses there, so I'm going to exit that, and then I'm going to say plus, but not the second parenthesis. That needs to stay. So plus log of 2 I like to show these because a lot of times students don't have much problems with the first part. They have a problem plugging this into a calculator. So I always think it's a good idea just to walk through this with you. So divided by, now we'll go ahead and parenthesize the denominator as well, even though it's not going to be absolutely necessary here because of the way this calculator works, but just to be on the safe side. So we'll say log 2. Again, we're going to want to exit that first close parentheses, and then minus 2 log 5. All right, and we should be finished. So take 5 seconds to review, make sure you punched everything in correctly. 3 log 5 plus log 2 divided by log 2 minus 2 log 5. You'll be surprised how many errors you would catch just by that 5 seconds that you spend. All right, so we get x is approximately, I didn't memorize that. If we go to, say, 4 places like we did on the other one, negative 2.1861. All right. Now, checking these, of course, is not always going to be super easy, but you can always get it done on a calculator. So you would go ahead and just type it in as you see it. So you would do the left side, like you would say 2 to the power of x minus 1, so negative 2.1861, and that's the left side. We have to do a minus 1 at this point. So that's all of the left side. We go ahead and hit enter. Now we want to just keep that on the screen while we go ahead and type in the right side. So 5 to the power of, this time we have 2 times negative 2.1861, and then we'll get out of that parentheses and type in plus 3. So let's make sure. So 2x plus 3. So 2 times negative 2.1861 plus 3. Now, before we even punch it in, I can tell you these won't be identical because we have rounded, correct? So, but they should be very close. So as you notice, they're very close but not identical. So that kind of error is expected because of the rounding. So we should be fine with this level of accuracy on these. Okay, so here we have one involving e, and of course when we want to solve these ones with e, even though we could use log base 10, when time comes to take the log of both sides, we'll go ahead and take the ln of both sides, or the log base e of both sides. So first we need to isolate this power of e. So we go ahead and divide both sides by 2. So we get e to the power of 3x plus 1 equals 1/2. Now we go ahead and apply the log base e to both sides, which, as you know, is also written as ln of e to the 3x plus 1 equals ln of 1/2. Now, if you remember, log base b of b to the x is just x, right? So that means that works for e as well. Log base e of e to whatever gives you that whatever as well, right? So, of course, when you write ln of e to the 3x plus 1, that is log base e of e to the 3x plus 1. So, so notice this side is just going to give you 3x plus 1. So you get 3x plus 1 equals ln of 1/2. And now we just need to solve for x. So we keep the 3x on this side. Let's go ahead and move the 1 to the other side. So we get -1 plus ln of 1/2. I wrote this -1 first just so it doesn't get confused whether we're subtracting 1 here or it's the ln of 1/2 minus 1. So to avoid any confusion, we can write it like that. So now we're just going to multiply both sides by 1/3. So in this manner, and of course here we will distribute. So be careful to never distribute into the argument of a log. So here we're just going to end up with x on the left side. On the right side we get -1/3 plus 1/3 ln of 1/2, like that. Again, this of course is the exact answer. If we needed to, we could always plug that into a calculator to get an approximation if we need it for a certain project. Okay, now we want to look at logarithmic equations, and they turn out to break up into two types. In one type of logarithmic equation, you have all the logarithms on one side of the equation, and in the other type, you get logarithms on both sides of the equation. Now, if we get the type with one side, we've already done some basic ones like that. So if we have more than one log on that side, we're going to go ahead and combine them all into a single log. And then we're going to just go ahead and convert to exponential form and then solve. Now, if the logarithms are on both sides of the equation, then we're going to want to simplify both sides in the same way, meaning make all the logarithms on each side, turn them into one log using the techniques we learned in the last couple of sections. And then we're going to basically end up with this kind of expression, because we're going to have just one log on the left side and one log on the right side. Then we're going to conclude from that that x must be equal to y. So once we've done that, then we're just going to have some simple linear equation usually, or could be quadratic, whatever, and then we go ahead and solve. And that's what we're going to be doing. So let's take a look at some actual examples. All right, so here we have a logarithmic equation, and we can see this is a log on one side scenario. So for those, if you remember, you simplify both sides as much as possible. If there are more than one log terms, you lump them into one logarithm using the laws of logarithms, and then you go to exponential form. There is no simplifying that's possible on either side. We go ahead and proceed with going into exponential form. So we know that the argument goes on one side by itself, and then you set up the power. Remember, the base remains the base, and of course all of the logarithm becomes the exponent, so 6 goes up here. So now, because we have a cube here and we want to get this x plus 4 out of that cubic situation, we can take the cube root of both sides. Now you can leave that as 2 to the 6, or you can write it as 6 to 4, either way. So x plus 4, that's the cube root of x plus 4 cubed, equals 4, and we get x equals 4 minus 4, so x equals 0. Now, the very, very least amount of checking that you should do with these, remember, logarithmic equations are mandatory check problems because things may go wrong. The things that could go wrong is that either a base or an argument could become 0 or negative and violate, and the base could also become 1. So we have to check for all those things. The base has to be positive, not 1. The argument has to be positive. So when we plug the 0 in, we notice that does remain positive. We should be okay, but that's just the argument check. So if you want to do a full check, you can go ahead and just plug it in. So we have log base 2 of, we plug in 0 for x, so we get of 4 cubed. We want to know if that's equal to 6, and that's log base 2 of 64. We want to know if that's 6. So what power of 2 gives 64? If you remember, that is in fact 6. So the left side is 6 and the right side is 6, so it passes and it works. So we know it's a solution. So the solution set contains not this, but your x value. So 0, one solution. All right, just to show you an alternative approach using the power rule, we could have also done this. Notice that we started out with that, right? We could have used the power rule right away to bring this 3 down. So we get 3 times log base 2 of x plus 4 equals 6. Now we can isolate the log term by dividing both sides by 3. So we get log base 2 of x plus 4 equals 2. Now we can go ahead and go to exponential form. So we get x plus 4 equals 2 squared. So you get x equals 2 squared, which is 4, and move this 4 from the left to the right, becomes minus 4. So once again, of course, we get x equals 0. So notice that you have some options sometimes as your approach. So either one is fine. I wanted you to see both, so there it is. Make sure you can handle these. Every time we finish a problem, just write it on a piece of paper. If you haven't tried it already, at least after watching it, make sure you can do it without having to look at all before you proceed. Okay, here we have a problem that at first glance might look like it's one of those log on both sides problems, but the fact of the matter is that since we can get this log on the other side and just have a constant on this side, it's actually considered a log on one side problem. The problems where you say you have logs on both sides are the ones where each term is logarithmic, because that way you can't avoid having logs on both sides. So let's go ahead and get that negative log x to this side as well. So we end up with log of x plus 15 plus log x equals 2. See? If you can manage to do this, then this is not considered a log on both sides type of problem, because you were able to get this number on this side. So now we go ahead and apply the product rule. Remember, log base b of mn is equal to log base b of m plus log base b of n. So we're using the product rule going from right to left. So in other words, we have a sum of two logs of the same base. We're going to write it as a log of the product of those two arguments. So we're going to get log of x plus quantity x plus 15 times x. It'll be easier if we write the x first, since it has only one term, like so. We get this. Now, this is where you need to be careful, because this is where we're ready to go to exponential form, but you have to remember, a lot of students make the mistake at this point. They just go to the next line and they write x times x plus 15 equals 2. You have to really watch out for that, because remember, there is an invisible 10 sitting right there. So when you move this to exponential form using the definition of logarithms, which is of course log base b of x equals y, if and only if x equals b to the y, then you end up with x times x plus 15, which is the argument which goes by itself on one side, and then you get the power 10 to the power of 2. So be very careful with that. So we have x squared plus 15x is equal to 100. We know how to solve these. We go ahead and move all the terms to one side and leave a 0 term on the other side. So this is a quadratic. We usually try this by factoring at first. If that doesn't work, then we can utilize either the method of completing the squares, or we can also use the quadratic formula. So in this case, it looks factorable. So remember, since the lead coefficient here is 1, we can use the big X method, where you're looking for two numbers whose product is -100 and whose sum is +15. Notice that since the product is negative, that means they're going to have opposite signs. And of course, the larger one is going to be positive to give us a sum of +15. All right, if we take a look at the prime factorization of 100 over here on the right, we know that we can start with 2, that gives us 50. Another 2 goes into 50 25 times. Now we have to move on to 5. 5 divided into 25 gives us 5. Finally, one more 5 gives us 1. On this side, only put primes. This is a nice substitute for the factoring tree. So we notice that we want two numbers whose product is -100, and so we can see that we have left 5 here, and these 3 seem to give us 20. That should work out, correct? So we want +20 and -5. Verify their product is -100 and their sum is +15. So that's going to be our factorization, and we have x plus 20. It's always useful to do a FOIL check. First times first is first, last times last is last. Inner product is -5x, outer product is +20x, and they add up to the middle term. Always check those three things to make sure you factored correctly. Now we apply the zero factor property. So we get either x minus 5 equals 0 or x plus 20 equals 0. So the left one gives us x equals 5, and the right one gives us x equals -20. Keep in mind that logarithmic equations are mandatory check problems because of errors that could happen. Here the bases are just 10. We don't need to worry about the bases. We need to make sure plug in either one of these will not make either one of those negative or 0. So we notice that 5 should work out okay. This remains positive when you plug in 5. That remains positive when you plug in 5. We'll still go ahead and check 5, but at least it passes the preliminary test so that we're not wasting time checking it. But for -20, as soon as I plug it in here, I notice I get -5. And of course here it becomes -20. So -20 we can reject already because it makes an argument negative. So, but 5 we'll go ahead and just double check. So we want to make sure that log of 5 plus 15 is the same as 2 minus the log of 5. So here we have log of 20. We want to know if that's the same as 2 minus log 5. As long as this equation here remains true, we can go ahead and move that to the other side. So we get log base 10 of 20 plus log base 5. We want to make sure that's 2. So of course, using the product rule, we get log of 100, 20 times 5, and we're checking to see if that's 2. And since this is log base 10, log base 10 of 100 is in fact 2, so we get 2 equals 2, so that checks out as well. So now we can confidently write our solution set to contain only 5. You see how important it is to check solutions of logarithmic equations because of the errors that could happen, such as with -20. So make sure, again, you can do this before we proceed. All right, so here in this problem, we do finally have a bona fide equation of the type log on both sides, because notice each term has a logarithm in it. So we go ahead and proceed by, we notice we have more than one logarithmic term on the left side. So we'll go ahead and combine those into one single logarithmic expression. The way we'll do that, of course, since this is a difference, we remember the quotient rule, which says the log base b of a quotient equals the difference of the two logs, the log of the numerator minus the log of the denominator. So of course we're going to be using this law in this direction. So we get log base 7 of 2x plus 4 over x minus 2 equals log base 7 of 4. So now we're going to use this other property which we discussed, that if the log of x equals log of y, and they're both the same base, b in this case, then that implies that x must be the same as y. So we have the log of this is playing the role of x here, and this 4 is playing the role of y. So we have two logs that are equal, the bases are equal, so therefore the arguments must be equal. So now we go ahead and set 2x plus 4 over x minus 2 equal to 4. We can throw a 1 under it to make this look now like a proportion, which of course means we can cross multiply. Want to remind you that log is not getting canceled or anything like that. Log by itself is some piece of wood in a river, okay? It has nothing to do with mathematics. Log always has a base, always has an argument. What is happening here is a sophisticated deduction based on the one-to-one property of the logarithmic function, which says if two outputs of a logarithmic function are equal, then the inputs must have been equal. So now we go ahead and cross multiply. We get 2x plus 4 equals 4 times x minus 2. So we get 2x plus 4 equals 4x minus 8. So let's move the x's to the right side. So we get 4x minus 2x equals 4, and we'll move the -8 to the left side. It becomes plus 8. So we get 12 equals 2x, or x equals 6. So a quick preliminary check tells us that doesn't make, plugging in 6 doesn't make any arguments negative. So let's go ahead and do a full check on it now. So we're going to check it. So we have log base 7 of 2 times 6, which is 12 plus 4, minus log base 7 of 6 minus 2, which is 4. We want to know if that's equal to log base 7 of 4. So here we have log base 7 of 16 minus log base 7 of 4. We want to know if that's the same as log base 7 of 4. And of course on the left side, applying the quotient rule gives us log base 7 of 16 over 4. We want to know if that's the same as log base 7 of 4. Of course, 16 over 4 is 4, so we end up with log base 7 of 4 equals log base 7 of 4, which is of course an identity. It is true. We don't need a question mark anymore. It's been verified. So we can write the solution set, which is the set containing the number 6. All right, so that's how we handle a log on both sides scenario. If this were plus, of course, that would have become a multiplication. So you'll see some of those on the homework with any textbook that you use, and you should be fine. So just follow procedure. Make sure you lump all the logs into one log on each side. And then once you have the log of one item equals log of one item, then those two items must be equal. Those two expressions must be the same because the logs are the same. So make the deduction and then solve the equation. And that's all there is to it. Now let's go ahead and look at some actual applications beyond just solving equations and see if we can handle them. All right, the first application we're going to consider is that of compound interest. Of course, this is as opposed to simple interest, where, like, let's say you invest $1,000 at 5% simple interest. Then at the end of the year, you're going to earn $50 on that $1,000. And when they want to calculate interest again for the second year, it's going to just be calculated on the initial $1,000. That's what we mean by simple interest. With compound interest, if you earn $50 in interest, then the next time calculations are for coming up for interest, they're going to calculate interest on the 1,000 and the 50. So this is what we mean by earning interest on interest. And this way, interest starts growing very rapidly, in fact, in an exponential manner relative to just basic simple interest. So here we have two scenarios. One is in which compounding is taking place a finite number of times, meaning there are a finite number of times each year where the interest is added to your account. And for that, we use this formula, A of t, that means the future value after t years is going to be the present value. This is also called the principal. And R here is the annual percentage rate. We usually write that in decimal form. N is the number of compounding periods. For example, if it's being compounded quarterly, that means 4 times. So N would be 4 here. If it were monthly, N would be 12. Daily, it depends. Most banks usually consider a day to be 360 days, so they would use 360 for that. And here, of course, they're N and T again multiplied together. So this is the formula we will use if we want to calculate how much is in an account with an initial investment or loan. So this is going to give the amount whether you're lending the bank, meaning investing, or a company, or borrowing. So the formula works in both directions. It all depends on whether you're the lender or the borrower. Okay. Now, if we compound interest all the time, every instant, of course, remember that means at each instant a much smaller amount of interest is going to accumulate, whereas the fewer the number of times, the larger each chunk will be. But if it is so that you are earning interest an infinite number of times per year, we call that continuous compounding. For that, the simpler formula A of t equals PE to the RT is used. Some people call this the PERT formula after the popular older shampoo PERT. But anyway, it's easier to remember. It's just the present value, or P, times, this is the same E we've been dealing with over the last couple of lessons. And it's the one that's approximately 2.7 to the power of RT. So the E here is a constant. Remember, this is not a variable here. And the values, these actually stand for the same things they did here. Future value after t years, of course, here that got left out somehow, and P is the present value. That means at the inception of the investment or loan, T being the number of years. So let's look at how we would use these two formulas. So here's where we have a scenario where $5,000 is being invested at a rate of 8% for 5 years. So we want to know how much will be in the account at the end of the 5 years in two scenarios. One is when it is being compounded, interest is being compounded monthly, and one when it's being compounded continuously. You may think this is because this is continuous, meaning interest is being earned all the time. This is going to be a lot larger than this. The actual fact of the matter is because you get bigger chunks in this situation at the end of each month than each instant in this case, they actually end up to be very close. This one will be just slightly higher. Now, if the numbers are large, of course, if you're dealing with a very huge initial investment, then of course the little bits add up. But for most investments, the differences are in the, pennies kind of category, as we'll see. All right, so on the left side, we're going to be using the formula for compounding, periodic compounding, which, if you recall, it was A of t equals p times 1 plus r over n to the nt. Now, here the p is of course the present value, which is 5,000. That means at the inception of the investment. And r is 8%, which we will of course write as 0.08. And n, it's being compounded monthly, so n is 12. And t is the number of years, which is of course 5. So basically, we're looking for a of 5. That means the future value after 5 years. All right, so we end up with 5,000 times 1 plus r, which is 0.08, over n, which is 12, to the power of n, which is 12 times t, which is 5. So if we simplify it, we just get 5,000 times 1 plus 0.08 over 12 to the power of 60. Of course, you don't really need to simplify it because you could just type the previous line into the calculator. So this was extra step, rather unnecessary. You can just type it in. I'll show you. So let's go ahead and bring up the calculator. Let's clean it up. All right, so just be careful how you type it in. So we start with 5,000. Okay, this didn't work. Let's try it again. So 5,000. And then we're going to go ahead and go times. On some calculators, if you just put parentheses, that's assumed to be times. But on some isn't. Like on this one, it is not. I have to put in the times. So now I'm going to open parentheses and put 1 plus 0.08 divided by 12. All right, we're finished with this. We're going to go ahead and exit out of the parentheses. And now we're going to put to the power of 60. Or actually, let me go ahead and, I promised I was just going to put it in its raw form. So 12 times 5. Because the calculator will take care of that for you. All right, and then we hit enter. And so we see how much there will be at the end of the 5 years. Let's go ahead and, with money, it never makes sense to go more than 2 decimal places because we don't have any denomination less than pennies. So hundredths is all you need to go to. So 7449.23. And of course, that's going to be in dollars. All right. Now let's see what happens if we compound interest continuously. As you know, for that one, we use the PERT formula. So A of t equals P E, of course, remember it's to the power of RT. So here we're going to have A of 5 because it's also for 5 years. P is the same, so 5,000. E to the power of R, which is also the same, 8%, so 0.08, times T, which is also 5. Notice we didn't have any use for the 12 here because we are not doing this periodically. This is continuous, so the formula changes. So let's see what we get when we type that into a calculator. Okay, so we're going to type in 5,000 times E, which is shift ln, remember, or second ln on some calculators. And now we're going to type 0.08 times 5. Enter. So there it is. Notice, in this case, a $10 difference. Just because the initial investment wasn't that small, you know, 5,000 is not nothing, but usually it comes out even less than that. But yeah, so definitely when there's a choice, you'll go with the compound, with the continuous compounding. $10 is $10, right? So 7459.12. All right, so that's how much we would have in the account if interest were compounded continuously. All right, so make sure you can apply these two formulas sufficiently. This one you don't need to memorize. If it's necessary, it'll be given to you. This one you do need to know by heart. So it's a simple formula to memorize. Just remember it's P times E to the power of RT. This next problem is known as a doubling time problem. Basically, you want to know how long it will take for an investment to double if interest is paid at the rate of 12% compounded continuously. So we're going to be using the A of T equals PE to the RT formula. Now, we can see R is 12% or 0.12, and we don't know the T. T is the unknown, and we don't know the principal, do we? But we do know one thing. We know a relationship between the present value or principal and what we want the future value to be. We want the future value to be 2p, twice the present value. So we want A of t to be 2p. So we're going to substitute that for A of t, and we have p e to the, we can substitute for r at least, 0.12t. Now notice what happens. You have p on both sides, so you can go ahead and divide it off, and this is precisely why we didn't have to have the initial amount. Notice that this problem could have easily said, well, how long will it take for $100,000 to double? And you would have had what? You would have had 100,000 here and 200,000 here, and you would have been able to divide both sides by 100,000. So this is why the interesting thing about it is it makes no difference how much the initial investment is. Whether it's $10 or $10 trillion, the amount of time that it'll take to double at a given interest rate, this is the only thing that matters. The amount of the interest rate is going to be the same. So again, whether you're investing $10 or $10 trillion, it'll take you the same amount of time to double your money. So here the simpler equation now is 2 equals e to the 0.12t, because the p's canceled out. So now we just have to solve this simple exponential equation. And remember, with these, we go ahead and take the log base e, since we have a power of e on one side. It's better. You don't have to. You can take log any base you like, but it's most efficient to take log base e of both sides. Of course, the right side, because of the rule that says log base b of b to whatever equals that whatever, just becomes 0.12t. And on the left side, log base e of 2 is just ln of 2. So now we just want to solve for t, so we go ahead and divide both sides by 12.12 now, or 1200ths. And we get t is equal to ln of 2 over 0.12. Now, of course, we want to know what that time is, so that doesn't give us much indication, so we'll go ahead and calculate that. All right, so we carefully enter the numerator. I'm going to go ahead and use it open with the parentheses. So I will go ahead and type ln of 2. Now I'm going to exit out of both of those parentheses, because when you type ln, it creates a new pair on its own. And we're going to go ahead and divide that now by 0.12. And we get approximately 5.8 years. So notice how interesting that was. Has nothing to do with how much you invest. It only has to do with the percentage rate. All right, so that's a nice, simple, but important problem. Make sure you can handle it on your own. All right, so the previous problem was in the category called doubling time. This one, we're going to be dealing with a concept known as half time. So here we have a certain radioactive substance which is decaying at a rate which can be explained by this exponential equation. Here, A0 stands for the initial amount. So when the clock starts ticking, let's say you have a certain amount, like in this example, 10 grams. So that would be your A0. So the initial amount of the substance. T is the amount, the number of years, and A of t will be the amount that will be remaining after the t years. Remember, this is going to, because of that negative exponent, is going to be an exponential decay curve, right? So basically here we have A0 equals 10. We're starting with 10 grams, and the first question we want to consider is how much will be left after 10 years. So that's basically calculation of A of 10, which is going to be A0, which is 10, e to the negative 0.0234, and for t we're going to use 10 as well, because they said 10 years. It's just, you know, accidental that these two numbers came out the same. There's no connection or relationship. This could have been 50. You would have had 50 here, and that would be 10. So just happens in this problem they're both 10. All right, so it's as simple as just plugging that into a calculator. So let's bring our calculator back, clear it. All right, so we're just going to carefully type 10 times, remember with this we have to put times, E, which is second ln. The nice thing is when you push second ln, it gives you the exponent position already, so you don't have to hit to the power of. In fact, if you want to get a value for e itself, you can do this. You can just type shift ln and then type 1. See? That'll tell you what e is, which you already knew. So if you ever forget what e is and you want to kind of see it, you can just type e to the 1. All right, that was a little tangent. All right, so let's go back. So 10 e to the power of negative 0.0234 times 10. Now I'm seeing something here which I'm not recognizing. I think I hit the absolute value key for some reason. Let me exit out of that. Let's repeat that. So negative, yeah, I see the absolute value is the second function of the plus minus, so somehow I accidentally hit that, so just be really alert. 0.0234 times 10. Take 5 seconds to check, make sure you've put everything in correctly. 10 e to the negative 0.0234 times 10. Then go ahead and hit enter. Didn't like something. Oh, you see where it is, right? This calculator is it's a great calculator, but a little touchy. I needed to put times there. Okay. So we end up with approximately 7.9. So remember, that's going to be an amount in grams. So at the rate that this substance is decaying, there's going to be 7.9 grams left after 10 years. All right, so the next question, we want to know what is the half-life of this substance. Right, so for this part, you don't really even need to know the 10. You just need to know that you start with an initial amount, A0. You want to know half-life is the amount that it takes to go from A0 to half of A0. Now, we could use those, but again, you can also use numbers, which will be much easier than bringing A0s into play, right? So we can just work, because it won't make any difference what initial amount you have. This is going to happen at the same rate. So we can just see how long it'll take to go from 10 grams down to half of it, which is 5 grams. So we're going to use, for A of t, we're going to use the future value, which with the future amount we want, which is 5. For A0, we're going to use 10. And of course, t is unknown. That's what we're trying to discover. All right, so we plug in. So for A of t, remember 5. For A0, the present value, we're going to put 10 e to the negative 0.0234 t. So again, we need to get e by itself. We'll go ahead and divide both sides by 10. So we end up with e to the negative 0.0234 t is equal to 0.5 or a half, either way. So notice, again, a simple exponential equation, and the best thing to do to both sides is to take the log base e. Of course, the right side becomes just negative 0.0234 t. The left side, that's just ln of 0.5. All right, so let me continue over here. So we get t is equal to ln of 0.5 over negative 0.0234. And we go ahead and plug that into a calculator to get the approximate doubling time. I mean, halving time, sorry. How long it takes for it to become from one amount to half that amount. I was still stuck on the previous problem. All right, so here we'll go ahead and parenthesize the numerator. So we'll type in ln 0.5. We'll exit those parentheses and we'll type divided by negative 0.0234, and then we hit enter, and there it is. This substance is going to take 29.6 years approximately, so nearly 30 years to go from its initial amount to half its initial amount. And this is just decaying at a natural rate, like many radioactive substances do. So that's quite a few years. So that's why we're worried about these kinds of substances being in the environment. All right, so for the final answer, for the half-life is 29.6 years. Again, the half-life of a substance is the amount of time that it takes for a substance to go from an initial amount to half that initial amount. All right. Make sure that you can do this. It's a good problem. Should be able to handle it. All right, finally, the last topic we're going to look at is change of base formula, because sometimes we have to deal with logarithms that are not base 10 or base e, therefore not represented on a calculator. So how can we deal with that? That's where this change of base formula comes in. So we'll actually prove it. We want to show that if you have log any base of a given number, then you can obtain that value, but taking log any other base of the same argument, as long as we divide by the log of the same base, new base of the base itself. Okay, so let's see how we can show this. So here's what we'll do. We'll give this guy a name. So let's just call it, so let's let log base b of x, let's just give it the name y. It could be any name. You choose your favorite letter, doesn't matter. All right, just a name that hasn't been used already. Okay, a letter that hasn't been used already. So now we'll go ahead and put that into exponential form. So we know that that means x equals b to the y. Now let's go ahead and take the log base a of both sides. So that means log base a of x equals log base a of b to the y. Now let's solve this equation for y. That means we're going to first bring the y down using power rule. So we get, therefore, log base a of x equals y times log base a of b. And now we can divide both sides by log base a of b, because remember, we're solving for y. And finally, we end up with y equals log base a of x over log base a of b. But you remember what y was? Y is log base b of x. So therefore, log base b of x, which is y over here, is going to be equal to this. Log base a of x divided by log base a of b. And we just proved the fact that we were trying to prove. All right, so there's a nice proof there for you. Being able to do something like this is going to give you mathematical muscle of world hero type strength. All right, so let's go ahead and use this new formula we just learned about on these two problems, and that's it for today. So we're going to compute log base 5 of 40 by using log base 10 logarithms. So let's recall the change of base formula. It says if you have log base b of x, you can compute it by using log of any other base of the same argument, as long as you divide it by log that same base of the original base. So we can take log base 5 of 40. Here the b is 5, the x is 40. So since we want to use base 10 logarithms, we're going to choose a to be 10. And on the top, of course, we need 40, and on the bottom we need log base 10 of the original base, which was 5. So of course we can just plug that into a calculator. Remember, that's just log of 40 over log of 5. Remember, when you don't put any number in the base position, it's base 10. So now we can plug that into a calculator and see what we get. All right, so we're going to type in, let's go ahead and parenthesize the numerator, log of 40. Actually, looks like there's some things there we don't want. Let's try again. So parentheses log of 40. Let's exit those parentheses, and we're going to divide that by log of 5, and we get 2.2920 approximately 2.2920. So of course we started with log base 5 of 40, so that's exactly what that should be. Well, approximately, right? We can of course test this, because if this is true, then 5 to the power of 2.2920 should be approximately 40, right? Let's check it. So we can bring the calculator back and we can type 5 to the power of 2.2920, and we notice that we indeed get something extremely close to 40. So that's how we can use a change of base there. So the last one we're doing log base 2 of 40. This time we're going to use base e logarithms. So we're going to take log base 2 of 40, and remember, we can write it as log any other base of 40. So in this case, we'll choose a to be e. So log base e of 40 divided by log base e of 2, the original base. So of course, you know log base e is just going to be ln on your calculator. So that's just ln 40 divided by ln 2. So let's go ahead and bring the calculator back. All right, so this time we're going to type in ln 40, exit the parentheses, divided by ln 2, and we get 5.3219 approximately. So approximately 5.3219. Let me make sure I wrote that correctly. 3219. Okay. So that, of course, is going to be log base 2 of 40. We can quickly check it by taking 2, raising it to the power of 5.3219 to see if we get approximately 40. It checked out on the left side. Let's see if we did this one correctly too. So we go ahead and type in 2 to the power of 5.3219, enter, and we do indeed get something very close to 40. So this one checks out too. So that's how you use the change of base formulas. So we learned quite a bit today. I hope you enjoyed it, and make sure you practice and be safe until we meet next time.